First we have to figure out the centroid of the whole shape. So we have the total area, 0.012 times the centroid is equal to the area of one of those two rectangles, 0.006, times its centroid. I put my coordinate system right here in the middle. And so you have 0.15, and then plus the area of the other rectangle. Its centroid is 0.31. And so you get that x, y is equal to 0.23. Okay, so what that says is the centroid is here somewhere, where this distance is 0.23. And so the centroid of this lower rectangle is at a height of 0.15, right? So the distance between the centroid of that rectangle by itself and the centroid of the whole shape then is 0.23 minus 0.15, and so 0.08. We're going to use that for the parallel axis theorem. So let me number these. Okay, so that's number 1. This is number 2. Its centroid is here. And these distances this distance is 0.08. And this distance from the whole centroid to the centroid of the top one is, 0.09, right? Oh yeah, because they're the same. That's right. It has to be because they each have the same area. Okay, so the moment of inertia of 1, that lower rectangle, is 0.3 times 0.02 cubed divided by 12, and then the parallel axis theorem part. So the area, 0.006, times the distance from that green circle, the center of that rectangle, to the centroid of the whole thing. So 0.08 squared. I2, this rectangle is oriented the other way, so this time you have 0.02. I did these backwards. I1, so this is the one that's cubed. For the second one, this is the one that's cubed. Plus 0.006 times 0.08 squared. And so the total is equal to I1 plus I2, and that's equal to I didn't listen before. What is that? 1.22 times 10 to the minus fourth meters to the fourth. Anyone have any questions about that? Okay, so now we have to think about the those stresses. So due to the internal tension, we know we have an XX stress that's equal to negative 40,000 divided by the area. And we get a stress value of this should be the total area. Sorry about that. We're dividing that tension force by the total area of the cross section. So this is 0.012. And you get a value of negative 3.33 times 10 to the 6th pascals. And now due to bending, this is the tricky one, because this is the one that varies along the cross section. One thing that we have going for us is we don't have to worry about anything side to side. All we have to worry about is on what horizontal line is this. Okay, so on any one of these red horizontal lines, the normal stress due to bending is the same. Okay, so where are we going to get a positive, like intuitively, so when we look at the bending moment diagram, the biggest absolute value of bending happens right at that midpoint at the roller, and it's negative, okay? So is the beam at that point bending up or down? Down, right? And so where are we going to get tension due to this bending moment, and where are we going to get compression? Yep. So because the bending moment is negative, we're going to have tension at the top, compression at the bottom. And we know that the formula we're looking at is this, negative my over I. Where are we going to get the biggest absolute value of y? At the bottom, yeah. To get to the top is only, what is it? Right. So y is 0.1 at the top, and y is 0.23 at the bottom. Okay. So we're going to have a bigger value in compression than we have in tension, absolute value. Right, if you look at this formula, everything else stays constant on this cross section. So two things agree that the biggest, the maximum XX stress in absolute value is at the bottom. And those are the absolute value of y is biggest at the bottom, and the one due to tension and the one due to bending are additive at the bottom, right? If we had this flipped upside down and we had a bigger absolute value of y at the top, then we'd have to calculate both at the top and bottom to figure out whether adding in the compression due to tension was enough to make up for that difference in y. Do you know what I'm talking about here? No? But you stopped listening, so it doesn't matter. So there are two things that, so first think about where the maximum absolute value of the moment due to bending is, okay? So first just think about that. Well, in our case, it's at the bottom. And the reason that it's at the bottom is because that's where the absolute value of y is biggest, okay? But it's also fairly big at the top. It's not as big in absolute value, but it's fairly big. So the question is, what happens when you add in this axial stress due to tension? Does this make it so that even in absolute value, the bending stress is smaller at the top? When you add them together, is it bigger at the top? Well, in our case, because the stress due to internal tension is compressive, and our biggest stress due to bending is also compressive, then we know that they're happening at the same place where compression is maximum. I don't know. Why don't you just sort of think through that on your own and let me know if you have questions with that. This isn't on the test, but this is an important thing to understand. So, so it's going to be at the bottom, and so we have the stress due to bending is equal to negative of -6226 times the y value of 0.23 divided by the I value that we just calculated of 1.22 times 10 to the minus 4. This is, the y value is negative. And so what do you get here for the XX stress? You're going to get a negative value times 10 to the 7. And so the final answer is the XX stress is equal to -3.33 times 10 to the 6 minus 1.17 times 10 to the 7th. And you get what? I guess bring that to a 4 and you get -1.507 times 10 to the 7 pascals. And if your material is susceptible to breaking in compression and tension, well, in this case in compression, then you need to check this value to see if that's something that is likely to do damage to your material. Okay. All right. So I have office hours today from 4 to 6. It's Wednesday, right? Yeah. So if you want to come work through practice problems or ask questions, I'll be around.
I can figure out how to prove your corollary geometry.
Oh, really?
Yeah.